Alright guys, so we're going to talk today about synthetic division, the remainder theorem, and the factor theorem. In class we've already talked about synthetic division, but I just want to give you a reminder here of how that works exactly. So synthetic division allows us to divide any polynomial by a polynomial that looks like a binomial, a linear binomial, something like x minus a number or x plus a number. And actually the original rule is really x minus something. So when we come down here and we see this, we're going to have to think about this instead of x plus 5 as x minus negative 5. That's going to be helpful for us. So we're going to take x minus 4 as what we're dividing by, and I take what I'm subtracting from x. So in this case that's 4. I'm going to put that 4 in a little box up here. Hopefully this is starting to ring a bell for you. Then I look at the coefficients of my original polynomial. I'm going to write them in order right here. Now, I go from x cubed right to negative 7x. I don't have an x squared term, so I need to use a placeholder of 0. So I'm going to write these numbers here. That's 1 for my 1x cubed, 0 for my x squared, negative 7 for my minus 7x, and then negative 6 for my constant there. I'm going to make a line here, and I start off just by bringing my 1 all the way down. Now this is the process that is going to repeat. I'm going to start with negative 4, multiply by 1, and put that answer right here, so that's going to be a 4. Then I add down. 0 plus 4 is 4. Repeat that process. 4 times 4 is going to be 16. I'll put that in there. Add down. Negative 7 plus 16 is 9. One last time, 4 times 9 is going to go right here, that's 36. And then negative 6 plus 36 is 30. So that's what I have. And I put this little box there, box it in, trying to get it to box in, there we go. And what I end up with is a depressed polynomial. So depressed means I started as an x cubed, dividing by an x is going to bring me to an x squared. So this is a x squared, an x, and a constant. The 30 is my remainder. So what I'd want to do is I'd want to write this using the coefficients that I have, the 1, 4, and 9. So it's a 1x squared now because I have to decrease my exponent by 1, plus a 4x, plus a 9, and then I'm going to add in my remainder as a fraction here. I'm going to have 30 over my original divisor, x minus 4. And that's my final answer for my first problem there. That's how we can do it. You can do it with long division too, but synthetic division is nice and quick. Just show you another example here using another example. Sometimes it's written not as a fraction but as a regular division. So I'm going to write that in the same format with my coefficients being 3 for the x to the 4th, 2 for the x cubed. I have no x squared, so I have to put a 0 there, 4 for an x, and I need a constant, so I'm going to have a 0 there as well. Now again, I mentioned we have to think about this as what is being subtracted from x, and since here I have x plus 5, what's being subtracted is a negative 5. I might want to think about that as x minus negative 5. So it's actually going to be a negative 5. It's going to go in my box up here. And now I just kind of bring everything down and follow that process. Bring down my 3, multiply by negative 5 gives me negative 15. Add to the 2, get negative 13. Multiply by negative 5, now we're getting kind of big, and that's just going to be what happens. That's okay though. That's going to be 65. Add down, that's 65. Multiply by negative 5, again we're getting real big, that's negative 325. Add down is negative 321, and multiply by negative 5 again is going to turn it positive. It's going to be 5, 0, 1605, I believe. It sounds like that makes the most amount of sense. Adding down gives me that 1605 in that kind of boxed off section there. So now I would just take that to get my answer, again, I depressed the polynomial. I started off as a 3x to the fourth, divided by x would give me to x to the third, so I've got 3x to the third minus 13x squared plus 65x minus 321 plus, and then I'm going to write this 1605 over x plus 5. Now, if I'm fortunate enough that I don't have anything remaining in these boxes here, that means my remainder is 0, which is convenient, and I would not have to worry about attaching this piece to the end. That's when it's going to be nice and easily divisible. Alright, so that's just a reminder of how we use synthetic division. We've done it before, so I just wanted to remind you of that. Now, the remainder theorem and the factor theorem are things that I can use in connection with this. So the remainder theorem is this kind of interesting thing where if we take a polynomial and divide it by x minus c, then the remainder is actually equal to f of c. So that means if we just use synthetic division and quickly look at the remainder, it'll be an easy way to get a result when we plug in a number into a function. So when we look at this, the example that I have here is to evaluate the function of the given value. I have f of x equals 6x cubed minus 5x squared plus 4x minus 5. Quite honestly, I don't really want to plug a 3 into each of those x's. That's going to be kind of a big process, so I'm not going to do that. I'm going to think about this instead as dividing 6x cubed minus 5x squared plus 4x minus 5 by x minus 3. And the way I would do that is through synthetic division. So I would write, don't want to move that. I'm going to have the 6, the negative 5, the 4, and the negative 5 as my coefficients, and I've got the 3. So now I'm going to bring everything down here, bring down the 6. 3 times 6 is 18. Adding that gives me 13. Multiplied by 13 gives me 39. Adding to 4 is 43. Multiplying by 3 gives me 129. And then adding to the negative 5 gives me 124. So that was pretty quick, pretty straightforward and pretty easy. And that 124 as our remainder is actually exactly what f of 3 is going to equal, which is amazing. So you can use this. It's sometimes called synthetic substitution because it's so quick and easy to do. And you can go ahead and take 3 and plug it in here and just check that that's actually what happens. It might be worth it just to make sure and maybe even double check my work. Maybe I made a mistake. But if so, you'll be able to find my mistake in the synthetic division and go from there. We can repeat this process using the 1, and just instead of plugging in a 3, we're going to plug in a 1. So I'll get rid of all of this here. We can see what happens. Kind of start the setup the same way. And again, I'm going to plug in a 1 here. So when I bring down the 6, 1 times 6 is 6, bring it up, add down is 1. 1 times 1 is 1, bring it up, add 4. 1 times 5 is 5, add down, and I end up with a 0. So I end up getting f of 1 equals 0 here. If I was doing this with synthetic division and not thinking about using it as a function, that would mean that if I took 6x cubed plus 5x squared minus 4x minus 5 and I divided by x minus 1, I would just have 6x squared plus plus x plus 5. I don't have a remainder to worry about. 1's not so bad to plug in here. I could plug in 1, and you can pretty quickly see that those won't change. You'll end up with 6 minus 5 is 1, plus 4 is 5, minus 5 is 0. So it does actually work out, but just definitely something that's worth using. So you can evaluate functions easily by using synthetic substitution, which is just a variation of synthetic division. All right, one more theorem. So the factor theorem is kind of connected to this, and sometimes it's beneficial to use synthetic division or substitution. Sometimes it's not. Sometimes we're better just plugging things in. But we can see the value of it either way. Basically, we can figure out if something's a factor of the polynomial if and only if the f of c is 0. So x minus c is going to be a factor if f of c is 0. Basically that means that the remainder of the division would also have to be 0. So we can use it with synthetic substitution if we wanted, or we could just plug in. So when I look at something like figuring out if x plus 4 is a factor of 5x to the 4th plus 16x cubed minus 15x squared plus 8x plus 16, I can try it with either method. So I'll try it with the synthetic substitution, and we'll see what happens here. So I think about what's being subtracted from x. So don't want to move that. Happens again. That's going to be a negative 4 is being what's being subtracted there. And coefficients are 5, 16, negative 15, 8, and 16. So I'm going to bring these down here. So let me give myself a little bit of space with where we can move. All right, there we go. So bring down the 5, multiply by negative 4 to get negative 20. Add down, that's going to be negative 4. Multiply is 16. Add down is 1. Multiply up to get negative 4. 8 minus 4 is 4. Negative 4 times 4 is negative 16. And lo and behold, I get 0, which means my remainder is 0. So that means that x plus 4, yes, it is a factor of that polynomial, which is good. That's convenient there. Because the remainder is 0, also known as plugging this in gives me 0. If I plug in a negative 4 for each of these x's, I'll end up getting the exact same result, where I get 0, which tells me that yes, x plus 4 is in fact a factor. Just make sure that because it's x plus 4, you're using minus 4 here. So now we'll just check it with x minus 1. So I'm going to think about what's being subtracted here. I'm just going to do it like I did before, where I kind of redo it in the same space. Let's get rid of everything there. And what's being subtracted from x is just 1. So I'll put a 1 here, bring down my 5, bring that up, and we'll see what happens. So I add down, get 21. Multiply by 1 is 21. Add down is 6. Bring that up, that's 6. 14. 14 gives me 30. 30 is my remainder. That's not 0. If I plugged in 1 here, you can see that I would end up with 30. If I plugged that again into each of these x's, I'd end up with 30. Which means that is x minus 1 factor? No, because I don't end up with a 0 here. So that's the big key. Alright, so hope that clarifies everything. I think it's pretty straightforward. You're really just using synthetic substitution kind of over and over again and drawing the conclusions from that. Basically, if you get a 0, that means there's no remainder. That means that it's a factor, which is nice when it works out nicely like that. But whatever you get for the remainder, that's what you would get if you plugged that value of c that you have in the box into the original polynomial. All right, thanks for listening.